My name is Rohit Dodia and today I am presenting a case study on metastability in digital systems, focusing on flip-flop behavior and synchronization using sequential circuit. This topic is extremely important in digital electronics because it directly affects system reliability and performance. So let's get started. First, introduction to digital systems. Digital systems process binary signals, meaning only 0 and 1. These systems are built using logic gates and memory elements. There are two types of circuits, combinational circuits and sequential circuits. Combinational circuits. Output depends only on current inputs. Sequential circuit. Output depends on current input and past state. Clock signal control operation in synchronous systems, ensuring everything happens at the right time. However, if timing is not handled properly, it can lead to unpredictable behavior or system failure. Role of flip-flops in sequential circuits. Flip-flops are the basic memory elements in digital systems. They store one bit of data and are used in registers, counters, state machines. There are four main types: SR, JK, D, T flip-flops. But their current operation depends on proper timings. If a timing is violated, they may enter something called metastability. D flip-flop. The most commonly used flip-flop is the D flip-flop. It has input D, clock CLK, output Q. It works on the rising edge of the clock. This means whatever value is at D during the clock edge gets stored in Q. Timing digital systems. Timing is everything in digital systems. Important parameters include clock period and frequency, setup time, hold time, propagation delay. It also faces issues like clock skew, clock jitter. Can affect performance if timing constraints are violated. It can cause errors, metastabilities, and system failures. Setup time. Setup time is the minimum time before the clock edge during which data must remain stable. If data changes too close to the clock edge, it can cause setup violation. As shown in the diagram, if the signal changes inside the critical window, the flip-flop may not capture the correct value. Hold time. Hold time is the minimum time after the clock edge during which data must be stable. If data changes too early, it can cause violation. The waveform clearly shows correct and incorrect timing scenarios. Timing violations. There are two main violations: setup violation and hold violation. In setup violation, data arrives late. In hold violation, data changes too early. Clock skew can worsen these problems. To avoid this, engineers use static timing analysis tools. If not fixed, this violation can cause errors, crashes, and metastability. Metastability definition. Now the core concept, metastability. It is a condition where the output is neither 0 or 1, but somewhere in between. This happens when setup or hold time is violated. Input is synchronous. The diagram shows the unstable state clearly. Metastable state behavior. In this state, output voltage is between logic levels. Resolution time is unpredictable. Eventually, it settles to 0 or 1. But the problem is we don't know when it is settle. It will settle. If it takes too long, it can affect the entire system. Causes of metastability. The main causes in metastability include: first is asynchronous inputs, clock domain crossing, also known as CDC, timing violations, and clock jitter and skew. Basically, whenever signals are not properly synchronized, this happens. Now, clock domain crossing (CDC). CDC happens when data moves between different clock domains. Since clocks are not synchronized, data may arrive at the wrong time. This is one of the biggest sources of metastability in modern systems like CPUs and FPGAs. Clock domain A and clock domain B have independent frequency and phases, making the relationship unpredictable. CDC is a major source of metastability and modern SoCs, FPGAs, and multi-clock digital systems. Proper synchronization circuits are required to safely transfer data across clock domains. Effects on system reliability. Unpredictable system behavior. Data corruption, system crashes and hangs, cascading failures, safety critical consequences. Metastable outputs can propagate through logic causing incorrect computation and state transitions. Incorrect values stored in register memory or transmitted across interfaces lead to functional errors. In severe cases, metastability can cause processors to enter undefined states or infinite loops. In critical systems like automotive, aerospace, medical, this can be extremely dangerous. Probabilistic nature of metastability. Mean time between failures, MTBF, failure rate increases with higher clock frequencies and data transition rates. Faster systems are not susceptible. We use MTBF, mean time between failures, to measure reliability. It cannot be completely eliminated and it can only be reduced. Faster systems are higher chances of faster systems have higher chances of failure. Exponential relationship doubling resolution time reduces failure probability by a factor of E. Need for synchronization. To solve this, we use synchronization techniques. Primary goal is prevent metastability from propagation through the system and causing functional failures. Ensure data integrity. Guarantee that data transferred across clock domains is captured correctly and reliably. Trade-off. Synchronization introduces latency. Typically 2 plus clock cycles but dramatically improves reliability. Standard practice. All modern digital designs with multiple clock domains require proper synchronization circuits. CDC verification tools check that all cross-domain signals pass through proper synchronizations. Two flip-flop synchronizer. This is a standard solution. It uses two D flip-flop in series. The two flip-flop synchronizer is the industry standard solution for the clock domain crossing. Circuit configuration: two D flip-flops connected in series, both clocked by the destination domain's clock. Path async input: FF1 may go metastable, FF2 samples resolved output, and then stable output. It provides exponential reduction in failure probability. MTBF improves by a factor where T is clock period. Working of synchronizer. Stage 1 FF1 captures asynchronous input. If input transitions near clock edge, FF1 may enter metastability. Resolution period. One full clock cycle provides time for FF1 to resolve from metastable state to valid logic level. Stage 2 samples FF1's output on next clock edge. By this time, FF1 has resolved to stable state with high probability. Probability analysis. If single stage MTBF is day 1, two stage MTBF becomes minus ET days, typically years or centuries. Output validity. Synchronized output is guaranteed stable, though delayed by 2 clock cycles. Latency trade-off. Application: CPU, FPGA, and communication. Basically, everywhere the multiple clock exists. CPU design: multiple clock domains require extensive synchronization for reliable operation. FPGA implementations. External interfaces: Ethernet, PCIe, memory operate on different clocks than internal logic. Communication system. Data transfer between systems with independent clock sources. Networking telecommunications. Memory controllers. Interface between processor clock and memory clock domains. Bus interfaces. AXI, AHB and other on-chip buses connecting modules with different clock frequencies. Advantages. Significantly improved reliability. MTBF increases exponentially from days to years or even centuries with proper synchronization. Prevention of data corruption. Ensure data integrity across clock domains, eliminating functional errors. Predictable system behavior. Eliminates random crashes and hangs caused by metastability propagation. Compliance with design standards. Meets industry requirements for CDC handling in ASIC and FPGA designs. Successful operation in safety critical systems enables reliable deployment in automotive, aerospace, and medical applications. So, in conclusion, metastability is an inherent phenomenon in digital system that occurs when timing constants are violated, causing flip-flop outputs to hover unpredictably between logic states. Setup time and hold time are critically parameters that must be satisfied for reliable flip-flop operation. Violation lead to metastability. CDC is a major source of metastability in modern multi-clock digital systems and require careful handling. The two flip-flop synchronizer is the standard solution for CDC, providing exponential improvement in reliability at the cost of two cycle latencies. Fundamental principle. While metastability cannot be completely eliminated, it can be effectively managed through proper design practices to achieve arbitrary high reliability. Thank you for watching. If you found this helpful, don't forget to like, subscribe and share.